Welcome astronomers to Chapter 14, Galaxies. In this chapter, we're going to be covering the Hubble Galaxy Classification, the distribution of galaxies in space, Hubble's law, what's behind active galactic nuclei, having a little tongue twisting going on there, and then take a look at the central engine of active galaxies. Okay, not the first, but the most prominent astronomer to study galaxies is a very famous person by the name of Edwin Hubble. I think all of us have heard about him in one form or another since we started taking our first science classes in grammar school. Throughout this class, certainly, we've been making note from time to time of images taken by the Hubble Space Telescope, so now you know who this space telescope is named after. But again, he was a very famous astronomer in the early part of the 1900s, the 20th century, who studied galaxies and tried to understand them and categorize them into some type of linear evolutionary fashion. And so there is an entire classification for galaxies named after him and after the work he had done. Okay? And so the first few slides in this lecture are going to just review his classification scheme, which is pretty easy and straightforward. But the results of that research led to a lot of other interesting insights into the structure of the universe on scales larger than galaxies. And so Hubble's work even has some impact on cosmology, which we will be studying in Chapter 16. In this slide here we have a pair of images showing the Coma cluster of galaxies, and we will talk later in the lecture about what a cluster of galaxies means. But what's different about these images from every other image that we have been looking at so far in this class is that within the pictures here, almost every object that is visible is a galaxy. And at some point when you do look through a telescope and you stare very, very deep into space, stars become too small for us to be able to see. And so what we do see, the smallest object that we can see in such deep photographs, are indeed galaxies. And so here we are taking a look at two images and seeing galaxies from the Coma cluster. Now, taking a look at Hubble's galaxy classification, he identified 4 different types of galaxies, and the first that we're going to take a look at are what we call spiral galaxies. Now, spiral galaxies are classified according to the size of their central bulge. And so when you take a look at these photographs, when we say central bulge, we're talking about this very bright spot here in the center of the galaxy, the brightest part. In this image it's shown much nicer. The halo is the bright area surrounding the most brightest part, and then the disk of the galaxy is this fainter band where you see the spiral arms. And so this spiral arm characteristic is what gives these galaxies their name. They're spiral galaxies because they have these beautiful arms sweeping away from the halo and the central bulge of the galaxy. And so it gives the appearance that the galaxy is rotating and spinning, and that appearance is correct. The galaxies do rotate and spin, and you can get a sense for the motion of the galaxy by just taking a look at how the spiral arms are organized. Okay, now let me just check here. Yes, this is what I was looking for. As you know, sometimes I get ahead of myself in my slides. There are 3 types of spiral galaxies according to Hubble's classification: SA, SB, and SC. So that's pretty easy to remember. S, of course, stands for spiral, and the ABC designation talks about the size of the central bulge in the galaxy. So SA has the largest central bulge, SE is smaller, and SC is the smallest. Of course, there are ranges of sizes that astronomers use, but we're not going to go over that in class. It's beyond the scope of our introduction. Because SA has the largest central bulge, it is rotating faster because it has the most mass. It also tends to have the most tightly bound spiral arms as a result. Types SB and SC are progressively less tight, But the correlation is not perfect. Sometimes we have a little incongruencies there, but for the most part, progressively SB is less tight than SC, and SC is less tight than SB. Okay, and I kind of pointed this again. The components of spiral galaxies we have the dust disk around the galaxy, the core, the halo around the core, the spiral arms, and the bulge is what you see, when you look at the galaxy side on. Okay, and so here, we get a good side view of a galaxy. This is the Sombrero Galaxy, and you can see here, this is the dust disk around it, and this is the core with the halo around it, and this is the central bulge. Okay, and some beautiful images of this galaxy. I'm just checking the notes underneath. The slide here has the infrared portion shown here in the second blow up here, with the dust content showing up as a false pink. Okay, moving on here. Similar to the spiral galaxies, is the second classification noticed by Hubble, is the fact that we have spiral galaxies that look like they have this giant bar down the middle of the galaxy through the halo and the core. And so taking a look at these photographs, you see these galaxies that certainly have these arms and spirals sweeping out from them, but there is this elongated bar that goes through the center of the galaxy, and the same is true here as it is here. And again, just like with the spiral galaxies where you have SA, SB, SC, here we have SB, as you can see here, and it's SBA, SBB, and SBC. Okay, the third type of galaxy is what we call an elliptical galaxy, and it truly is elliptical. It does not have spiral arms or a disk. They do come in many sizes. You have small ones and very large ones. The small ones, of course, would be dwarfs. That's the name astronomers tend to use, and then the large ones would be called giants. And the giant ellipticals usually have trillions of stars, whereas the dwarf ellipticals can have less than 1 million. Okay, ellipticals contain very little gas, cool gas. They have hot gas, but they contain very little cool gas and dust, which is very different from the spiral galaxies because they have that dusty disk, that flattened disk that goes around the core and the halo, where ellipticals do not have that. So sometimes astronomers have a very difficult time, if they're looking at a galaxy edge on, seeing the spirals in a spiral or a spiral barred galaxy, because they're looking at it from the edge instead of from a top or a bottom view. And one of the ways that astronomers can tell that they have a spiral versus an elliptical galaxy, if they're looking at it edge on, is to see how much gas or dust is present in the galaxy, which we can get through our spectral diagrams, spectral analyses. And so if they take a look at a galaxy edge on and it doesn't have much cool gas or dust, usually they would interpret that as being an elliptical galaxy, even though they can't see it from plan view. And so because you don't have a lot of this gas and dust, there is very little evidence in elliptical galaxies for the new creation of stars. All right, remember, we've spent a tremendous amount of time speaking as to how stars were formed and how you needed to have an interstellar cloud of cool dust particles that had temperatures of about 10 degrees K. And if you have galaxies that have very little of that, well, then you're not going to have new star formation. So most of the stars in elliptical galaxies tend to be older stars, whereas in spiral or spiral barred galaxies, the stars can be old, but you have a good number of young stars forming as well. Elliptical galaxies, as I said earlier, do have large clouds of hot gas that extend pretty far beyond the visible boundaries of the galaxy. Some of those gases can be picked up in ultraviolet X-ray, not sometimes gamma ray, but mostly ultraviolet X-ray. These hot gases do exist in the spiral galaxies. Alright, and so taking a look at them through Hubble's classification, he gave 7 subdivisions for the ellipticals that was based according, of course, to their shape. And so he started with almost spherical circular ellipticals that gave them a characterization of EO. And if you had very elongate ellipticals, like how I did that, elongate ellipticals, they had a classification of E7, and so in between there you would have any kind of variations. And so here on the slide we have an E2 elliptical, and E3, you can see it's starting to stretch out, whereas the E2 looks a little more circular. And here's an E5, which is broadening out pretty well. And if you wanted to have a combination of spiral and elliptical, such things do exist. And so here we have SO, which would be S for spiral, and SBO. And SO or lenticular galaxies would contain a disk and a bulge, but no interstellar gas and no spiral arms. And so they're, in many ways, an intermediary between E7 ellipticals and SA spirals in their properties. And you can also have an SBO galaxy that is similar to an SO galaxy, except there's a bar of stellar material extending beyond the central bulge. So of course you can have some I'm thinking the word comparisons, I don't know why. Of course you want to have some blending between the galaxies, and so these classifications are meant to accommodate that. And then finally, the fourth type of galaxy Hubble noticed was what he called an irregular galaxy, and he called them irregular precisely because they have a very wide variety of shapes. Now we are familiar, I remember being introduced to them in grade school, to what has been termed the Magellanic Clouds. And the Magellanic Clouds are visible in the southern hemisphere. Unfortunately, we cannot see them here in the northern hemisphere. And they were discovered by Magellan on his travels through the world, across the world's oceans. And so navigators used them. They could see them with their naked eye at night, but used them to help with their navigation across the oceans. But the Magellanic Clouds are irregular galaxies. Okay, and so they're very close neighbors of ours. They're part of our local galaxy group. And here we have some pictures of them. Here the small and large Magellanic Cloud, and then you have some blow-up pictures of them shown here. So here we have some pictures of some irregular galaxies. Okay, here's a beautiful image here, but of course you can see how irregular it is. It looks like you have a central region and there are some dust clouds around it, maybe some star-forming regions here. This is a galaxy called AM 0644-741. And I will tell you, I am cheating. I'm reading the note because that is quite a mouthful. And unless you're studying this thing every day, I don't know how anyone would remember that. But that is the name of the galaxy, and astronomers do feel that it is about to collide with the galaxies in its group here, just so you know. And then here on this side is another galaxy. This is NGC 1569, and this irregular galaxy has an explosive appearance, and so this might be the result of recent star formation and nova creation. So, but there's just some pictures of irregular galaxies there for you. Alright, and so to tie all of this together, the next slide shows a table that summarizes the galaxy properties by type. And so I'm going to zoom in here a little bit. Well, before I zoom in, here along the top we have the different types of galaxies: the spirals, barred spiral, the elliptical, the irregular. I said there were 4 types here. They combine the spiral and barred, so it's 3 listed up here. It doesn't matter so long as you remember there is a spiral and then there are barred spirals. And then on the downward side here you have the shape and structural properties, the content, the gas and dust formation of stars, and how the stars in the galaxy move. And so there's quite a bit of text here to help distinguish between the different types. And so this is a good cheat sheet to use. I would pay attention to this one. These tables are great to help study with. Okay, so pay attention to that and know the differences between the spiral and the barred spirals, the ellipticals, and the irregulars. So what Hubble was able to do after he classified all the different types of galaxies is he was trying to find an evolutionary relationship between them. And so he felt that you could start off with an elliptical galaxy, and through star formation, gravitational attraction, and the usual culprits and suspects for how things are done in astronomy, go from one type of galaxy to another. And so he created what astronomers affectionately call the tuning fork organization of galaxies. And it is an interesting and a mnemonic way of memorizing or remembering how the galaxies are classified. And so he starts off with an EO elliptical and goes through the progressively more elongate ellipticals to finally get to the SO, which is the combination between the spirals and the spiral bars and the ellipticals. And then you have the pure spirals up here, the spiral bars down here, and then irregular is left here. So again, the diagram is suggestive to an evolution of galaxies, but try as astronomers may, they were very interested in showing that there was an evolution of one galaxy type to another. The data just has not been forthcoming to support that hypothesis. And so at this point in time, astronomers do not have the data they need to show that there's any kind of evolutionary arrangement or relationship between the different types of galaxies. So it is, again, a very interesting way of organizing the classification scheme, but there is no additional meaning behind this that suggests they're connected in any way. Okay, so we've reached our first concept check for the chapter. Okay, in what ways are large spirals like the Milky Way and Andromeda, which is one of our neighbors, not representative of galaxies as a whole? Okay, so considering Hubble's classification system and the discussion of all the different types of galaxies out there, this shouldn't be too interesting a check to be able to talk about on discussion board. Okay, so now we are going into the discussion of the distribution of galaxies in space. Now, one of the ways that astronomers are able to measure the distances to galaxies, again, remember when we opened up the lecture, we spoke about how when we're looking very, very deeply into space, really all we do see are galaxies because the stars are too far away and too small, and therefore their apparent brightness is too low for us to be able to see them. And so when we have such large distances, we have to come up with some interesting ways of measuring these distances, and Cepheid variables are one way of doing that. Now, we did not get into the details of Cepheid variables in this class, and I'm not about to do it right now, but a Cepheid variable is a star that does vary in its brightness in a predictable way, and in a way that can be measured by astronomers. And again, if you can measure the variability in luminosity of a star, not only can you measure its distance because of its luminosity, but you can also measure anything with respect to time because of the periodicity of its brightening and darkening, brightening and darkening, brightening and darkening. So Cepheid variables are these types of stars that do occur and are found in some but not all galaxies. And when we do see them, we can use them to help us figure out measurement of distances. And so usually Cepheid variables are good up to about 25 megaparsecs away. Much further than that, and they are too dim for us to be able to see, and so we need to find other methods to measure the distances to galaxies that are further away than about 25 megaparsecs. Now what I want to do is zoom in on this picture here because I want to show you the 6 different snapshots here. You can kind of see them in this, at this magnification, if you will, if you pay close enough attention. But this is a Cepheid variable star in the spiral galaxy M100. It's in the Virgo cluster, which we'll discuss in a few slides. And you see this dot here. All right, let me do it this way. Right, the top arrow of my mouse shows a little dot. That's the Cepheid variable there, and you can see it here, and over here, and here, and here, and here. Okay, and I'm going to zoom in now. Scroll up a bit. Zoom in a little more. Will that let me? Yes, okay. And so here it is again. Here's the variable here, 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 and here. Okay, now these pictures were taken at different times during 1994, and it is a 24th magnitude variable star that has a change in its luminosity by a factor of 2 about every 7 weeks. Alright, so astronomers know when it's going to change in its variable, in its luminosity. And so you can see, you know, as you go from panel to panel here, the differences in brightness of that star. Now again, taking a look at the larger picture, you know, this is the box here where this variable star is. I have to zoom out, I realize, because I think it's outside of what is being recorded. Okay, so here is the box here for showing that region of space where this tiny little Cepheid variable is present, and you can see just, you know, at this magnification up here, you can't even see that variable, and you really do have to zoom in to be able to catch it and its varying brightness. And so again, this is the reason why Cepheid variables only work up to a certain distance before you need to find some other standard of measurement with which to measure distance with. Okay, so I'm going to zoom out again. Just there we go back to the regular viewing. Okay, and so, you know, if you have a galaxy that has no Cepheid, or if the galaxies are further away than 25 megaparsecs, again, you need to have a new distance measurement technique in order to use. And so there were two astronomers, one by the name of Telly, the other by the name of Fisher, that were able to provide a new methodology for measuring galaxy distances beyond 25 megaparsecs that use their Doppler effect to assist them. And so basically the idea here, as we already know, is that if you have a rotating object in space, the part of the object that is moving towards us is going to be blue shifted, and the part of the object that moves away from us is going to be red shifted. And so they took a look at the galaxy's rotation speed, because rotation speed is related to rotation speed will give you the Doppler effect, because you see the rotation, and if you see how fast the red and blue shifting is moving, that gives you the speed of the rotation. And the idea here is that the rotation speed is directly related to the mass of the galaxy. The more mass of the object, the faster it spins. So if you have galaxies that are spinning very fast, they have a lot of mass. And if we can figure out from the Doppler effect and the rotation speed the mass of the object, which of course then is also related to its luminosity, we can use the mass of the object and its luminosity to figure out the distance. You can use the mass and gravitation, to the gravitational formula, to figure out the distance. And again, you could also use the luminosity, because how luminous it is, and then its comparison with its apparent brightness, also give us a measurement of distance. And so the Tully-Fisher relationship used the Doppler effect and the rotation speed of galaxies as a method to help us figure out how far away things are. And so again, taking a look at this diagram here, we see this galaxy. It is rotating. I was doing it the other way. It is rotating in this direction here. So if you are a viewer, this portion of the galaxy is being moving away from you and it's being red shifted. This is moving towards you and it's being blue shifted. And so if you combine that blue and red shifting, you're going to get a frequency curve in which it's very broadened as a result of how fast the rotation is going. And so if you have this curve here, then you can again convert that into a mass and luminosity relationship and then figure out the distance as a result. So the Tully-Fisher relation has been used quite successfully with studying the distances to galaxies that are further away than 25 megaparsecs. Now, another thing that astronomers have been able to use is something called a standard candle. Okay, and a standard candle refers to objects in space whose absolute magnitude is known. And so if they know the absolute magnitude of such an object, and this is true for all specimens of this object, they always have the same absolute magnitude, then you can determine, again using the luminosity, the distance using their apparent magnitude from how far away they are from you. And so they call these things standard candles. Okay, they're just candles, if you will, light sources that have a set luminosity, and so any kind of variations in their luminosity are a result of how far away they are from you, not because of any kinds of changes. And one type of astronomical object that is very useful for a standard candle is a type 1 supernova. Okay, most of these supernova all explode for about the same reason, and it doesn't really matter what the star is made of, what the circumstances were. We're talking about the death of a star, and this energy is just given off, and the luminosity is fairly consistent no matter where you are in space, how far away you are, what the object, the star, was made of. The luminosity is about the same. And so for that reason, a type 1 supernova has been used as a standard candle. We have, on the magnitude scale, a designation for what the supernova magnitudes, luminosity magnitudes are, and therefore any shifting away from that absolute magnitude tells you something about the distance. Okay, but that approach is what we call using a standard candle. All right, and so I believe there's a homework or a quiz question to this effect, and so pay a little attention to this concept because you'll see it on the homework and or the quiz. Alright, and so here we are visiting this inverted triangle again that talks about all the different ways of measuring distance in space. And if you recall back to the beginning of our class, we talked about radar ranging to help figure out distances within our solar system, or from the Earth towards the Sun. So radar ranging only gets you within about 1 astronomical unit. After that, we can use stellar parallax, which is good up to about 200 parsecs. We talked, when we discussed stars, about spectroscopic parallax, and that distance measurement can take us out about 10,000 parsecs away from us. Variable stars, again, we didn't discuss this too much other than a quick 1-2 sentence definition a few slides back, but using variable stars, Cepheid variables, can allow us to measure objects up to 25 megaparsecs away. And then we just discussed briefly the Tully-Fisher method and the use of standard candles. And the Tully-Fisher method gets us to about 200 megaparsecs, and standard candles gets us to about a gigaparsec. So we have 1 or 2 more ways of measuring distance way out there in space. But my recollection is we don't discuss those now until the next chapter when we talk about cosmology. All right, but now we have a lot of different tools at our disposal for measuring distances the further and further out into space you go. Okay, so now using these techniques, we can see up to about a gigaparsec into space. Now, getting back to the distribution of galaxies, we live, as you know, in the Milky Way galaxy. That is our home galaxy. And taking a look at these diagrams here, I'm going to show the blow up here. You've seen this diagram before when we were talking about the Sun, but now we're talking about the Milky Way galaxy. I'm going to blow in a little bit for you so you can see it. And so if you treat the Milky Way galaxy as the center of the universe for the time being, and it's in the center of this bullseye diagram, what you see here are the names of other galaxies that are close by to us. Alright, again, this is the plane of the Milky Way galaxy. Before we used it as the plane of the ecliptic. This is the galactic plane, central plane. And so these galaxies are above the Milky Way plane, below it, to the side, wherever. But these are the nearest galaxies to us. Okay, now just moving down here, this diagram shows this space here. So here is the Milky Way, and here are the galaxies close by around us. Okay, and then within there, here we have some other galaxies here as well. And so this is what we call the local group. Okay, the local group is about 45 galaxies that are within about 1 megaparsec of our own Milky Way galaxy. So it's about 45-50 galaxies, and they call it the local group. So our galaxy is not alone in space. It has friends and colleagues all around us. And these galaxies all interact with each other gravitationally. They kind of travel together as a group, Yes, they have their own individual motions, but they kind of stay in close association with each other um, as part of the local group. All right, so I'm going to zoom out here a little bit just to get back. There we go. All right, and in the local group there are 3 spiral galaxies. There's our own galaxy, the Milky Way, which some astronomers think is a barred spiral, but you know, when I was in school I was told it was a spiral, and so I have a prejudice for that at this point. The Andromeda Galaxy is a spiral, and another galaxy by the name of M33. Alright, and so again, these and about 45 to 50 other galaxies form the local group. Okay, now when we have such a grouping, this is what we call a galaxy cluster. I know a few slides back we introduced the term and I said we would discuss it, and here we are. So a galaxy cluster is a group of galaxies, such as the local group, held together by its own gravity. And so galaxies do not tend to form in isolation in space, they do tend to form in clusters. And so galaxies aren't necessarily evenly distributed through space. They are clustered together, and then the clusters also have superclusters and mega clusters. But you know, individual galaxies do tend to just group together to form clusters. Okay, now outside of the local group, there's another nearby galaxy cluster. Again, we talked about, you know, superclusters and megaclusters. The Virgo cluster is another galaxy cluster that is close by to the local group. It is much larger. The local group, as I said, contains 45 to 50 galaxies. The Virgo cluster contains about 3,500 galaxies. And so the Virgo cluster is about 17 megaparsecs from Earth. A lot of large spiral and elliptical galaxies, you know, so there's a lot to be seen. But again, here are 2 photographs. Here is a blow up showing the local, the Virgo cluster here, but again, a tremendously large number of galaxies in that group. Here we have another galaxy cluster called Abell 1689. It's another very large cluster. It's about 1 billion parsecs away, but does contain thousands of galaxies as well, just like the Virgo cluster. But again, the beauty of this picture is that virtually every patch of light in this is a galaxy, is a separate galaxy. So again, you know, the distance we're dealing with here is 1 billion parsecs. So, you know, stars can't be seen from that distance. If you are looking at a star in this photograph, that star is in between the Earth and this galaxy cluster. Alright, so the star has to be much closer for us for it to show its little face in the picture here. So every image in this picture here is a galaxy. And so if you just take a minute to appreciate that, you know, and let the awe of it strike you. You know, when we look out into the night sky, we think we just look at stars. And then if you think of our solar system and our place in the Milky Way, and we're just, you know, in the suburbs on one of the spiral arms of this fairly large galaxy spinning around, and how small we are, and then take a look at this photograph and see here thousands of galaxies. That's all you're seeing here, and inside each and every one of these galaxies are billions of star systems which have planets. Whether or not they have life on them, we don't know, but it just again leads you to stand in awe at how large the universe is, what's in it, and our place in it. So quite a beautiful photograph in my opinion. So just to continue on here, that leads us up to Hubble's law. Okay, so as I said, you know, Hubble spent a good portion of his career you know, classifying galaxies, trying to understand, you know, why they were shaped the way they were, what made them tick, how they were related to each other, if at all. And so one of the things he noticed in studying the galaxies is when he started taking a look at their spectral lines, is that all of the galaxies, with just a few nearby exceptions, or I should rephrase that, with a few exceptions within the local group, that's it, okay, seem to be moving away from us, or what we call receding. Alright, so everything, every galaxy we look at is just moving away from us, and of course you can see that again by taking a look at their spectral lines in the Doppler effect. And so all of these galaxies have a redshift, in their spectral lines away from us. Okay, now we can take a look at the redshift. Or what Hubble was able to do is, because he studied all these galaxies and measured the redshift away, and some of the galaxies he knew how far away they were from us, he was able to correlate, redshift. When we take a look at redshift, we know that the galaxy is speeding away from us. And so we can calculate a velocity through wavelength for how fast it's moving away from us. But that also correlates into a distance. Okay, so you can, looking at redshift, not only calculate that the star is moving away from us and how fast it's moving away from us, but you can use redshift to actually tell how far away it is from us, the distance. And he did this by plotting his data on a graph, which I'll show you in the next slide, and then just figure out the distance. But again, by using the redshift of the galaxies, he did see that the galaxies were moving away from us, and they called this universal recession. All right, and so here we have a couple of nice spectral lines shown for these different kinds of galaxies. Here we have the galaxy cluster in Virgo. Here's a cluster in Ursa Major, the Large Bear, Corona Borealis, Bootes, and Hydra. And I get a kick out of this because these are all constellations that are visible in the August night sky if you happen to go outside and try to identify a few of the constellations. I was out the other night and I was able to see Ursa Major, Corona Borealis, and Bootes in the star Arcturus. So these are, should be somewhat familiar names if you know a little bit about the constellations. But again, these constellations do have galaxy clusters in them, and so Edwin Hubble studied these and took a look at their spectral lines. And what you're seeing here is a measurement of their redshifting. And so taking a look here at the Virgo cluster, the Virgo cluster is fairly close to us. It's the next cluster away from the local group. And so I'm going to zoom in here so we can take a closer look at the spectral lines. Okay, these white ticks on the spectral lines are just laboratory controls. All right, but here's the spectral line for the Virgo cluster, and they are able to see here, this yellow dot is referring to this little spot here, that it is away from the control here by that amount. So this is, I guess, the Earth. This is the location of the Earth, and it is redshifted away from us at this position here. When you take a look at the cluster in Ursa Major, here's the distance in megaparsecs. I'm sorry I didn't point that out before. So the Virgo cluster is about 17 megaparsecs away. Ursa Major is about 210 megaparsecs away. And you can see that based on the control, Ursa Major is redshifted even more. Here is Corona Borealis at 310 megaparsecs. You can see the arrow showing the extension of the redshift. A galaxy cluster in Bootes, you can see the redshift here, and then I'm going to scroll up, and then here is Hydra. You can see the redshift over here, and Hydra is about 870 megaparsecs away. Alright, and so you can see how the further away the galaxy is, it is redshifted more and more. These numbers underneath the spectral lines here are the radial velocities in kilometers per second. So this is how fast that galaxy is moving away from us. And so what he is showing here, and I'm going to scroll down so you can get the view of the whole slide again, is that you can see the distance here. The distance gets further and further away from our solar system. You have the larger redshift, but take a look at the radial velocities. So not only is the star redshifting away from us by a greater percentage, but the velocity is getting faster the farther away you are. So it's kind of almost like, the farther away, the faster you run trying to get away from us, like they're trying to escape. Okay, but this was a very important correlation and a very important discovery that we really didn't understand until Hubble took a look at it, was the fact that the farther away from us you were, the galaxies or objects were redshifted more, but they were traveling faster. Okay, and so this was a very important correlation, and is shown here on these two plots. Okay, and so what we have here is a very simple graph. You have on your x-axis the distance in millions of parsecs on both A and B graphs here. We have 500 million parsecs. I have a billion parsecs here. Here is the recessional velocity in kilometers per second, 25K, 50K, 75K. And we have the plotting of a few stars here in A, I'm sorry, a few galaxies here in A, and then a lot more galaxies here in B. So just to show that, it doesn't matter if you're plotting a few or many, the relationship is the same. And the relationship here is the straight line that shows a one-to-one correlation between how far away you are and what the recessional velocity is. So again, the further away you are, here they're at 1 billion parsecs, you have a much higher recessional velocity. The closer you are to us, you have a much lower recessional velocity. So this was a very important discovery by Edwin Hubble and his work on galaxies, and the fact that there's a one-to-one correlation as evidenced by this straight line. It's not a parabola, it's not an ellipse, it's not a circle, it's a straight line. So there's a one-to-one correlation between distance and recessional velocity. Okay, so when you have that type of relationship where you have a straight line, the slope of that line, all right, so if we go back to take a look at this, how steep that line is. The slope could be a very gentle slope. Maybe you have a line that's gently sloping. If you follow my mouse trailing across the graph here, it's just a very gentle slope here. You could have a very steep slope if it goes up very high and steep like this, like a cliff. But instead we have a line here that's kind of in the middle. It's like a 45-degree angle almost. Alright, but that's what they refer to as the slope of the line. So that slope is controlled by the relationship between the distance and the recessional velocity. And so if you have a gentler slope, what it shows is that you can go much further and the speed doesn't kick up as fast. Or if you have a much steeper slope, you can say your speed is really kicking up, and even though you're not moving very far away. But that's not what's being shown here. This very mediocre 45-degree slope is showing that there's a one-to-one relationship between how fast you're going and your velocity. And so the slope of that line is a constant. Okay, it doesn't change. And that is what they call the Hubble constant. Hubble's constant, they gave it a symbol of HO. But what they're saying is the recessional velocity that you see on the y-axis is related to the distance times this constant, times the slope of a line. And so really this equation just represents the equation for a straight line. Okay. Now Hubble, when he first calculated his constant, came up with a number like 300 objects were moving away from us at a velocity of about 300 kilometers per second per megaparsec. But from continuing studying of Hubble's work throughout the years, astronomers have revised that figure. They had to take other things into account that Hubble wasn't aware of at the time. He didn't have the data required. And so the currently accepted value for Hubble's constant, HO, is equal to 70 kilometers per second per megaparsec. Okay? I don't think I have any questions on your test or quiz that requires you to remember that HO is 70 kilometers per second per megaparsec. And my general rule for these types of classes is I don't necessarily have you memorize numbers and such. But I do want you to know what Hubble's constant is, what it's representing. You just don't have to go around memorizing numbers and stuff. But, please be aware of what it is. Okay? So 70 kilometers per second per megaparsec is the currently accepted value, and that's saying something. It's the currently accepted value. There's been a lot of tweaking and changes to the value of Hubble's constant. There are some difficulties with it and some problems, so what astronomers are saying is that in the future, with more data, Hubble's constant may change again. So much for being constant. But what we do know for right now is that 70 kilometers per second per megaparsec, it works good enough for large distances. Okay, so the farther away the object is, Hubble's constant works better. And the reason for that is there's some random motion to stars and galaxies that needs to be brought into consideration that, kind of causes the speed at which objects are receding away from us to vary a little bit. And so if the objects are further away, such random motions tend to become more and more background noise because you're dealing with such large distances. So as a result, Hubble's law tends to work better for large distances. So we don't tend to use Hubble's constant for things very close to the Earth. We tend to use it for objects that are very, very far away from us. All right, and so that puts the final step on this inverted triangle for the techniques we have to measure distances in space. Congratulations, you made it through all these different techniques. Okay, and so we started off again with radar imaging and stellar parallax, and now we're sitting here talking about Hubble's law. All right, and so Hubble's law again is used. It's better to be used for objects that are more than a gigaparsec away, or 100 million parsecs, however you want to think of it. But that is pretty much the top of this inverted pyramid here, and what we can use when we want to figure out the distances to objects very, very far away. All right, and so that leads us to our next concept check. How does the use of Hubble's law differ from the other extragalactic distance measurement techniques we've seen so far? I'm sorry to that in this text is in there again. Remember, I'm pulling this stuff from another textbook that you guys aren't using for the class. So, but you know what I mean. Okay. Moving on to the next slide, we talk about active galactic nuclei here. Now, about 20 to 25% of the galaxies that are out there don't fit too well into the Hubble classification scheme. They are far too luminous. There's too much going on in the core. There's too much mass. There's too much luminosity. And so these are what we call active galaxies. All right, not that a normal galaxy isn't active, it certainly is, but these active galaxies are out there. All right, and so they're different not just from the luminosity, but also the type of radiation, which is, you know, part and parcel of the luminosity. All right, and so if you take a look here at this diagram here, you should recognize this curve here. This is a black body radiation curve. And so a normal galaxy, because it has wavelengths that emit heat and temperature controls a lot of the functions of the luminosity in a normal galaxy, does have a black body approximation to its radiation curve. Active galaxies don't behave that way. Active galaxies don't fit the black body curve. You can see here the curve for an active galaxy. Here is intensity on the y-axis. This is a very active in terms of the intensity of radiation that it emits. It's much more intense than the black body curve maximum here for a normal galaxy. And again, you know, it does also span the whole spectrum of wavelengths, but you know, it just has a very, very different type of curve. And so what this is saying is that, again, the radiation that's coming from this active galaxy, the luminosity, is really not being controlled by temperature or temperature variations. It's being controlled by something else. And so we're going to get to that something else. This is a case of my leading you on here to something a bit of a surprise, or maybe not, but some, you know, more interesting topic down the road. But there is some source of energy in these active galaxies that is different than that found in normal galaxies, and so we see it in the luminosity and the types of radiation that they emit. And so, and when you find out what's in the middle of these active galaxies, you'll be like, no wonder they call it an active galaxy. All right, and so, so about, you know, a quarter of the galaxies that are out there don't fit into Hubble's classification. They're what we call an active galaxy. Okay, now again, I said that the radiation from active galaxies isn't controlled by temperature, so these are what we call, this is a non-stellar radiation. Remember, temperature due to nuclear fusion inside the cores of stars is what creates the pressure to keep gravitational collapse at bay. So stellar radiation does follow the black body curve. It is very important to star formation and the lifetime, the evolution of stars and how they die. But radiation from galaxies isn't related to temperature, and so it's called a non-stellar radiation. Okay, now many of these luminous galaxies do have these outbursts of star formation, and it's probably due to interactions with their neighbors, and so some of them are also called starburst galaxies, but we'll talk about that a little later on. And again, the galaxies that are very active are so because of things happening in the galactic center, which we'll talk about. All right, so here's a picture of an active galaxy. This is, or an active galactic nuclei galaxy. It's NGC 7742, okay, and it kind of does look like a fried egg. So you have the center part of the galaxy here. You can see how bright it is in the very, very center, and it certainly has a different color here. And then surrounding it are these rings of blue areas that are where we're forming stars, okay, but we have a very, very bright yellow core here, and so that's a picture of an active galaxy. Now there are three types of active galaxies depending on the type of radiation that they're emitting or some of their properties, okay, and these are called the Seyfert galaxies, named after astronomer, of course, radio galaxies, and many of you have probably heard of quasars already, but we'll talk about those and what that word actually means, okay? Now, just beginning with Seyfert galaxies, you know, when you first take a look at a Seyfert galaxy, it looks a lot like a normal spiral galaxy, okay? And so, at first, you know, astronomers didn't pay too much attention to it until Seyfert came along, but he noticed that they were thousands of times more luminous. And so he wanted to investigate them. And so here's one of the ones he investigated. It's called the Circinus galaxy, and it does have that bright core in here. It's about 4 megaparsecs away from us. It's one of the closest active galaxies. And here we have a chart that shows its variations in its intensity through the years. So we started measuring this galaxy in 1970. We're still measuring it today, and you can see that there are times when the galaxy has high levels of intensive radiation, then it drops down a bit, then it has another spike, and then it drops down again, up a little bit, down, up. And so Seyfert galaxies do exhibit fluctuations in the amount of intensity that they irradiate. And this is important. It says something because in order for these fluctuations of radiation to be even visible to us, what it's saying is that the galactic core for the Seyfert galaxies has to be very small, because you got similar to the sun. Any radiation that comes out of the galactic core has to fight its way through a ton of material. Now in the stars, in the sun, when you have radiation that forms in the core, it has to go through the radiative zone, it has to go through the convective zone, then it has to go through the photosphere and the corona and the transitional zone, and it takes sometimes thousands of years for a photon created in the center of a star to make it up to the photosphere. Well, you can imagine how long it takes for radiation from the center of a galaxy to, you know, galaxies aren't stars. Galaxies are hundreds to thousands of parsecs wide. And so for a photon or for radiation to escape from a galactic core, it has to go through a lot. And so usually we don't see fluctuations in radioactive intensity when we study the cores of regular galaxies. But with Seyfert galaxies, we do see the fluctuations of radiation. And what this is telling astronomers is that the core of a Seyfert galaxy must be fairly compact, less than about a parsec across, and that is the only way, when the radiation escapes through such a small nuclei in the galaxy, that we can see these fluctuations. And so this was a very significant discovery that astronomers made when studying galaxies, that took a spiral, something that looked like a spiral galaxy, and it turned out to be something else. So it's amazing what, you know, the different types of radiation can show us if we, you know, choose to look at objects through different lenses. Okay? And so, whoops, I guess again I got ahead of myself, I apologize. So, you know, here again, the rapid variations in the luminosity of the Seyfert galaxies indicate that the core must be extremely compact. Okay. Here we talk about radio galaxies. All right, and radio galaxies are called so because they emit radiation very strongly in the radio portion of the spectrum. So understandably so, we catch them or view them by using radio telescopes. Okay, it's not that all radio galaxies are invisible. Many radio galaxies, do exhibit release radiation in the visible spectrum. So a lot of radio galaxies do have, you know, we can't see them through optical telescopes, but they also have this component where they emit radiation in radio waves, and that is what is invisible to our optical telescopes. So again, we take a look at these galaxies, and they look like normal regular galaxies, and then we turn the radio telescopes on them, and wow, you've got the galaxy's top 20 being beamed right back at you. And you can see that here in these pictures. So here in A, this is the radio galaxy Centaurus A, and here this is the visible spectrum that you can see here. It looks just like a regular kind of spiral galaxy. You have the dust cloud, the dusty disk. Here we have the core and the halo and the bulge around it. But then you turn on the radio telescope, and this is what you get here. You see, this is a false color image, of course, but these are plumes of radio radiation just being emitted from the top and the bottom, if you will, from the galaxy. Okay, and so again, this is invisible to the naked eye. You only can see this if you have radio receptors turned on. And then if you take a look here at this close-up, we're going to take a look here at this gas plume here emitting in radio waves. This is it right here. I'll zoom in for you just to show you a bit of a better picture there. Alright, so I can zoom back here, back to normal. Whoops, I'm trying. Okay. Alright, and so these are radio galaxies. Okay, now here's a couple more pictures of radio galaxies. Here we have this contour map of the radio galaxy M86, and the radio emissions are coming from this bright central nucleus, which is surrounded by a less intense radio halo, which is why what the contour map is showing here, the differences in intensity of the radio waves coming off of the galaxy. Okay, and so what we see here, the radio waves are superimposed, the contour map is superimposed on top of a visual image underneath it. Okay, but again, you have this very bright, core here that is exhibiting in the visual spectrum, but there's also a radio component to it as well. And so when you have this kind of situation in which you don't have these plumes of radio waves coming off the galaxy like you saw in the previous slide, but you have this contour map surrounding it. This is, what they tend to call a core-dominated radio galaxy, where the radio waves are being emitted all around it. Now, there has been some talk that core-dominated and radio-low galaxies might be the same thing. It's just a difference in the angle that they're viewed, so what you're seeing is something different. Okay, and so here we have this diagram here showing this galaxy here. You have the central energy source in the galaxy right here, and it is emitting radio waves along this line here. These are jets of radio waves. And so depending how you're viewing this, if you're looking at it edge on as this person is here, again, radio waves tend to be invisible to the naked eye, so you're not necessarily going to see them, the radio waves. So, excuse me, I'm sorry, after a while my throat gets scratchy, I gotta pause and cough, I'm sorry. Here you will see through the radio waves and get to see the central energy source. But here, because this person is looking at it not edge on, but from a top or bottom perspective, if they have the radio wave being picked up, they can see the lobes here. So depending on how you're looking at it, it gives you a different view. Now, many active galaxies have jets, and if you take a close look at these pictures here, you can see these jets. Here we have a giant elliptical galaxy, M87, also called Virgo A, and if you take a look at the central region here, this blow up, you see it with a jet projecting out from it, and a close-up of that region shows the jet more clearly here. Now the bottom part, C here, is an infrared image of M87's jet. So what it's saying is that it's giving off wavelengths that would correspond to heat at this point. But these jets are the sign of one of the signs of very active galaxies, and usually these things occur when you have collisions with other galaxies and other types of stellar matter. Now finally we've gotten to quasars. Now most of you have probably heard of quasars, if not through science fiction, through some reading of textbooks or astronomy magazines. And quasar was a short form of quasi-stellar object. So that's what a quasar is. It's just an abbreviation of that term. Now quasars are very unimpressive in telescope view, even if you are from space. Having a telescope in space, I mean. Taking a look at this band here, certainly you see a lot of very bright and luminous objects here that are catchy of the eye, and you would think that a quasar, for all their famousness, would be something like this in nature, but no. The quasar is this very, very faint and dim object here that when you take a look at this area, you get the blow up here and you see this is right here is the quasar that has a luminous jet matter. So I'm sorry, the quasar is right here, and this is the luminous jet matter. But the main body of the quasar is star-like in appearance, and they are extremely bright, quite luminous. But the problem is that they are tremendously, tremendously far away from the Earth, and for that reason they are very, very dim. And so quasars are some of the farthest objects away from the Earth. They are at the edge of the universe, if you will, and are also extremely, extremely old. And so that is the reason why they are so faint. You can barely see them here. But their luminosity is known. They're very, very bright, and for that reason they're one of the standard candles that astronomers tend to use as well. But a quasar is considered to be an active galactic nuclei. It's considered to be some type of accumulation of star matter in a galaxy type scenario, and so it's considered or lumped with the active galactic nuclei. Now eventually one of the reasons that quasars came to astronomers' attention obviously wasn't because of its visibility in telescopes from Earth. As you can tell from the previous slide, you can barely see it. You can't see it usually. But in taking a look at the spectral lines for those areas in space, quasars were picked up because of how odd their spectral lines were. And for very, very long times, for decades, astronomers just could not explain how odd the spectral lines for quasars were. Taking a look here is the spectral line for a quasar. This here is a comparison line or a comparison spectrum, and you can see it looks quite different. There's a tremendous amount of fuzziness. You do have some lines, but they're very faint and they're fairly broad. And so, you know, again, astronomers just couldn't explain this until finally someone did figure it out and was able to figure it out. And what they realized is that there was nothing particularly different about a quasar spectral line or spectral composition. It was just tremendously redshifted. And so the hydrogen lines here, the hydrogen lines for beta, shown here, gamma and delta, were shifted over towards the red end of the spectrum when they should have been over here. And so the tremendous shift towards the red wavelengths is what caused all the confusion. And once astronomers figured this out, they realized that a quasar's spectra were, you know, not abnormal. They were just tremendously redshifted. But this was very, very important, because to have such a red shift shows that they are, of course, moving away from us at tremendous speeds, but they are also extremely, extremely far away from us. Now, the redshift in the spectral lines is going to become a tool that astronomers use, as we will discuss in the next chapter, for being able to measure distances that are very, very far away and objects that are very, very old. And so we will revisit this topic of taking a look at very distant and very old astronomical bodies and talking about their redshift. So we will come to revisit this. So here is another image that shows how unimpressive quasars look in optical images. Okay, here we have the night sky, and you can see some beautiful galaxy. Here's a beautiful spiral galaxy here and some other galaxy bodies here. And there is a quasar in the picture, and it can be seen by taking a look at this arrow here. And I'm going to make the west, let me see here, I'll make the north pole of my mouse here, point right at it. Yeah, right there, that tiny faint little thing there is a quasar. So again, you know, this is very unimpressive. We're using a telescope to take a look at this, and we can barely notice it amongst the plethora of other galaxies in the photo. But again, we know that these quasars intrinsically are some of the most luminous objects in the galaxy. And so to be the most luminous object in the universe, actually, never mind the galaxy, and yet to be so faint, just indicates how far away they are. Okay, and so this leads us to, I think, I might be lying to you again, I do believe this is our last concept check for the chapter. The energy emission from an active galactic nucleus does not resemble a black body curve. Why is this important? Okay, so we'll discuss it more on discussion board. Okay. So here we're taking a slightly closer look at redshifts, again because it does become an important topic in discussing cosmology and the age of the universe and very, very distant objects far away. And you know, so we're going to just take a little more detailed look at redshifts and the theory of relativity and what we call look-back time. And so it's predominantly a text slide here so you can read it, and I'll read through the important parts of it with you here now. Okay, now again, we've been talking about redshifts in beams of light as just fractional increases in wavelength, and this is true, but there is slightly more, there's some more significance to the redshifts that we measure of objects than that I've been letting on to in the course so far. Redshifts are measured directly, and distances can be calculated from them using Hubble's constant. Now you know already that that is an uncertain constant, that there have been some difficulties with it. And so therefore astronomers would of course prefer to quote redshifts rather than use them to calculate distances, because if you take a redshift you're making an actual measurement using scientific equipment of an intrinsic property of a stellar object. And if you take that measurement, then we are plugging it into an uncertain equation, or using an equation that has an uncertain constant, and therefore you're introducing a possible source of error into the distance you're calculating. So to avoid that, what astronomers prefer to do is just quote the redshifts. And so when we talk about objects that are very old and very far away from us, and we start talking about objects of a cosmological nature, astronomers usually drop the whole distance discussion and just quote redshifts. And so redshifts in those types of contexts have become synonymous with distance, and it isn't uncommon for astronomers at all to be sitting there saying, oh, I have an object that's 0.05 redshifted, and it means something in terms of distance to astronomers who understand what they're taking a look at. And so in future discussions throughout this chapter and the next chapter on cosmology, you're going to see us start to talk about distances by just talking about redshifts instead of plugging the data into an equation where there's some questions. Now the next concept that will become more predominant in our discussions is something called the look-back time. And the look-back time is the time when light was emitted from a distant object. Now remember, light has a finite velocity. It travels at about 3 times 10 to the 8th meters per second. And so this finite speed of light means that it still takes a tremendous amount of time for light from very far away objects to cross the universe and meet us. So when we look at objects that are very far away and we are looking at their light and we say something to the effect that it is 14 billion or 12 billion light years away, what you are really saying is that you're looking into the past. You're looking today at how that object looked 12 billion years ago. And so this is what they call the look-back time. It is the time when the light was emitted from a distant object, And for very distant objects, it is less than the redshift would indicate. The distance to this object is, or the distance to this object is less than the redshift would indicate. And the reason for that is, yes, it has taken, for example, 12 billion years for the light from a quasar to reach us here at the Earth. But in the meantime, okay, that object is still moving in space with the rest of the universe. That object has receded in the 12 billion years that it has taken to reach us. And so for that reason, the distance is not quite as far as we would calculate it to be if we were to take the redshift and then calculate a distance. And so that's also another argument for why astronomers would rather just talk about the redshift and not try to calculate a distance measurement when we're dealing with objects that are extremely far away and extremely old. So again, we'll discuss this in more detail in the next chapter, and I think you'll become a little more comfortable with the idea once you give it a little more thought. Okay. And so just talking about what powers the engine in active galaxies, and this is really what we've been leading up to, and I have a suspicion some of you may already know the answers, especially if you're watching some of the astronomy specials on TV. But if you don't, and this will be a bit of a surprise for you, it'll be an interesting surprise to find out what powers the central engines of active galaxies. So when we take a look at active galaxy, the nuclei of active galaxies, they have some or all of these properties listed on the slide. They all have a high luminosity, much brighter than a normal galaxy. And the energy that they are emitting is non-stellar. It is not coming from starlight or from stars in a star factory. The radiation curves from active galaxies are not black body radiation curves. They have very different curves, and so this energy does not come from a star. The energy output can be variable. It does fluctuate over time, which does indicate a very small nucleus. Again, we had touched on this briefly. Any kind of energy emitted from a nucleus has to travel through the nucleus into the galaxy and through space before we can see it. And so if we are able, for galaxies that are active and very far away, to be able to pick up on variations in its energy output, it must indicate that the nucleus in this active galaxy is very small in order to be able to allow that energy to escape and for us to be able to measure it. Because remember, if any kind of energy moves through gas or clouds in space, it is going to impact the light we see and how it comes to us. Active galaxies have jets and other signs of very explosive activity, and they also have broad emission lines when we take a look at their spectrum, which indicates that there's rapid rotation. And we've been able lately, and this has been all over some of the TV astronomy specials, been able over a couple of decades to map the locations of stars within these central regions, and we've actually been able to see their rotation, revolution around the galactic center and how fast they're moving. So that's another line of data that I neglected to put on the slide here. Alright, so these are some of the properties of active galactic nuclei. And so the leading theory right now for the energy source in an active black hole is, oops, I gave it away, I'm sorry, for an energy source in an active galactic nucleus is, ta-da, a black hole. I'm so sorry. And so it's a black hole that's in the center of a lot of these active galaxies. We found out in the meantime that there's black holes in many of the galaxies, including, we think, our own. And this black hole is surrounded by what we call an accretion disk. Okay, and in some ways, if you think about it, it does make a lot of sense. Black holes have a lot of the properties that we discussed on the previous slide, and when you have such a large gravitational attraction pulling matter all around it, no wonder there's a galaxy's worth of matter rotating around a black hole. Now, black holes also have strong magnetic field lines around them that help to channel particles, and that's part of the reason for the jets that are being extruded perpendicular to the galactic plane or the dust plane, or even the magnetic axis. All right, this isn't too unlike the aurora borealis we see in the northern sky. When the sun's radiation hits our magnetic fields, it just follows the magnetic lines of force to come back into the earth. And so it's very similar. If you have charged particles, the magnetic field will control where they go. Okay, so but again, the central engine of an active galaxy is a black hole. And so just something, maybe it's no surprise to you, but when I was growing up, black holes were this exotic feature. They had just described it when I was in grammar school and high school, and there were these scary places, and I was like, oh wow, black holes. And now we're finding that they're everywhere, which in some ways does make a lot of sense. Galaxies tend to be locations where you have tremendous star formation, but if you're going to conserve matter even in space, you have to have some place to destroy it. And so a black hole certainly will do that for you. So I'm just going to zoom into the slide here. I got to zoom back out here. I don't have the capability of sliding here to the side. But again, here is your active galaxy, and there's a black hole, and the gravitational attraction of the black hole is controlling the rotation of the accretion disk and the rest of the galaxy around it. And then magnetic lines of force perpendicular to the galactic plane help shunt away charged particles and create jets of high-speed particles moving out of the galactic plane there. So I'm going to reduce back. There we go. Alright, and so in an active galaxy, the central black hole may be billions of solar masses, which tells you how massive they are. And the accretion disk around the black hole are whole clouds of interstellar gas and dust, and they may radiate away as much as 10 to 20% of their mass before disappearing. So this is what is going on in the center of an active galaxy. Here's a pair of images that does show some evidence for a black hole in the center of this galaxy, NGC 4261. It's a combined optical radio image of this giant elliptical galaxy, and so here is the optical image here, and the radio image is picking up the jets that are extending from it. Now here in the B panel in this slide here is a close-up of photograph of the galaxy's nucleus, and you can see that it's this glowing disk. It's about 100 parsec diameter disk surrounding this bright hub that is thought to hide a black hole. And so so this is some of the evidence that astronomers are using to confirm the hypotheses that black holes exist in the center of active galaxies. Okay. Here we have the central portion of M87, and it is showing rapid motion, which you would expect in the accretion disk around a black hole, and you can see it in the spectral lines here. We have a shift to the red on one side, and on the other side here we have a shift to the blue. So it's showing one area moving away and one area moving towards us, and if we have this measured over time, then that gives us a velocity. Okay, and now one of the things that's interesting about black holes, and that caused us to take our time, if you will, in discovering that they were possibly present in the cores of active galaxies, is the fact that when you do have black holes, they radiate mostly X-rays and gamma rays, which is how we pick them up to begin with, because again, black holes take in all light, all matter, and once that matter and light and radiation passes the event horizon, it does not escape. And so there is no visible light to be seen. But sometimes a black hole will take in so much matter that it will radiate out X-rays and gamma rays. And so this is how we tended to find them. But where galaxies are concerned, if you have black holes in the center of galaxies, again, remember that that radiation has to make its way through the galaxy itself, the dust clouds, and then through space. And so oftentimes the X-rays and gamma rays are absorbed by the gases in the galaxies and then re-emitted using longer wavelengths, and so they're kind of reprocessed and the dense clouds around the black hole. And so it took us a while to realize that when we were seeing infrared or radio signals coming from the centers of these galaxies, it was reprocessed radiation from the black holes. So taking a closer look here at the diagram on the slide, I'm just trying to blow it up for you here. So here we have the accretion disk here. You have the supermassive black hole. Here we have a dust cloud around the black hole in the galaxy. And so, moving out in this direction here, you're going to get broadband radiation of all types, from radio waves all the way through X and gamma rays, because there's very little interference or reprocessing along this line of direction from the galaxy. But any radiation coming through the galaxy here is going to be absorbed and then re-emitted as longer wavelengths, and usually we see this as an infrared heat radiation. Okay, so just to zoom back out and take a look here, and then again, just talking about the charged particles that follow the magnetic field lines coming from a black hole. Any kind of charged particles that are following magnetic lines emit what we call a synchrotron radiation, and that it's just, it doesn't make a new form of matter. It's just, this radiation is given off from the particles moving really quickly along the magnetic fields of line. And so again, this is radiation that's emitted from electrons on magnetic field lines, not radiation that comes from thermal activity or nuclear fusion in the core of stars. So this is a non-stellar type of radiation, and again, this is coming from the active galaxy. Now, taking a look at the chart here with the frequency and the intensity of the radiation, here you have your black body curve for your thermal radiation. We've seen that a lot in the class so far, but when we're taking a look at a synchrotron radiation, it's completely different. You see that it's a straight line, and its intensity and frequency decrease in this direction along the slope. And so it's just very different. It's not a thermal type radiation, it's not a stellar type radiation, but this is what we're finding inside of the active galactic cores. Alright, and so that's the end of chapter 14. Just to summarize it up again, remember that Hubble classified galaxies according to their shape. So we have spiral galaxies, barred spirals, elliptical, irregular, and so, some people group the spiral and barred together to make 3 types here. I tend to separate them, so it doesn't matter so long as you remember spiral, barred, elliptical, irregular. In order to be able to measure distances of distant galaxies, they're starting to get, we're starting to talk about objects that are fairly far away from us. We use a concept called a standard candle, and it's just, a luminosity source that has a standardness or uniformness to it that doesn't change regardless of the interactions going on with the object. And so if you have the luminosity being fairly constant throughout the evolution of this object, then any change in apparent brightness is because of distance. And so you can use the standard candle to help calculate the distance away from the object you're examining. And so we've talked about type 1 supernova, Cepheid variable stars. We didn't really talk about our Lyrae stars, so you don't have to worry about that, but I should really take that out of the notes. The Milky Way lies within a small cluster called the Local Group, and nearby we have the Virgo cluster, which is a much larger cluster that contains thousands of galaxies. Hubble, with his work on galaxies, did find out that galaxies that recede from us faster are the ones that are farthest away. So the farther away they are, they move faster, and that has become known as Hubble's law. Now, to wrap up, we have active galaxies that are far more luminous than normal galaxies, and their radiation is not of a stellar nature. And there are 3 types of these galaxies: Seyfert galaxies, radio galaxies, and quasars. And they all have these tremendously small cores, which we now know are black holes, may emit high-speed jets, which is, all different kinds of broadband radiation escaping out perpendicular to the dust disk surrounding the black hole. And, any infalling matter that goes into the black hole converts to energy, which helps power up the galaxy. Okay, so that is chapter 14, Galaxies in a nutshell. Again, an entire course could be taught around galaxies and their importance in the universe. But in a survey course, this is just a quick preview of what astronomers know to date on these stellar objects. Okay, so one more lecture to go, everyone, cosmology, and it's a very interesting lecture. A lot of fun in many ways. We talk about the Big Bang and where astronomers think we're going and how the universe is going to end up. And so it's an interesting end to the course. Okay, so one more lecture to go, and summer session 2 will be done, and you will have all completed astronomy. All right, so again, if you have any questions, please don't hesitate to email. I do apologize if there's any kind of breaks in the text or my talking during the lecture. I did try to get this recorded today while the baby was napping, and he got up, and so I had to break and come back later. So I do apologize if there's an inconsistency in the talk somewhere there. All right, so my best to you all, and I'll see you on Wednesday with chapter 16. Have a good night. Thank you.